Hello, abstract math. I hope you're having a pleasurable time during this period of time that is not break time. Hopefully, as you watch these videos, you're not texting, you're not on Facebook, you're not whatever else you do online. I don't want to even think about it. But hopefully, you're being diligent. You're taking good notes, just as always, and you're preparing yourself to do some homework assignments, which are coming up soon. Today, I'm going to be covering one of the most important theorems in mathematics, the binomial theorem. And before we do that, let's pray, and then we'll get things started. Father in heaven, we always want to ask for your wisdom as we approach some new venture. And Lord, for all of us, this is a new venture. Watching our classes on YouTube rather than being able to see each other face to face. I pray, Father, that face to face time will come soon. But Lord, in the interim, we thank you for these means of being able to continue to stay focused and continue to learn. And Lord, I pray for your wisdom during the minutes of this class, that you'll help me to be clear, you'll help the students to be clear, and you'll cause everybody to be encouraged to give me a call if they have questions. That Lord, that becomes bigger and bigger as we're unable to meet together face to face. So Father, glorify yourself in the coming moments now. In Jesus' name, amen. Okay, let's start off with what I promised, the binomial theorem. Before we do the theorem itself, I want to show you or remind you, for some of you this is a reminder, of what's called Pascal's triangle. Pascal's triangle is very simple to create. It has ones all the way down the isosceles, the legs that make it an isosceles triangle. So 1, 1, 1, 1, 1, 1, etc. But in each one of the rows, each one of the horizontal rows, an entry is the sum of the two entries above it. So 1 plus 1 is 2. This entry here, 1 plus 2 is 3. 2 plus 1 is also 3. 1 plus 3 is 4. 3 plus 3 is 6. 3 plus 1 is 4. And so on. The next row would be 1, 5, 10, 10, 5, 1. And of course, it's an infinite triangle. Now, the rows are numbered from 0 on. Row 1, row 2, etc. And then the slants are going to be numbered, so that this is slant 0. This one is slant 1. This is slant 2, etc. So the slants go down along this way, okay? And I'll be referring to them that way. So row 2, slant 3 doesn't exist. In other words, if n equals the row number and k equals the slant number, then k is always less than or equal to n. So row 5, slant 3, would be this row, and then the slant is 0, 1, 2, 3. So row 5, slant 3 is 10. That's going to be notated as 10 with a 3 under it, no line, it's not a fraction, and it's read ten choose 3. And we'll be finding out during the course of this lecture why I call it 10 choose 3. It's a combinatorial coefficient, however, and we're going to be dealing with it quite a bit. So let's get familiar with being able to construct Pascal's triangle for any number of rows. With that under our belts, I want to make another definition that is probably familiar to you. Definition, n with an exclamation point after it. Does not mean n. It means n factorial. And n factorial is equal to n times n minus 1 times n minus 2 all the way down to 1. So it's read n factorial. And we're going to make a special definition for 0. 0 factorial, we're going to define to be 1. Why? Because we can. It's actually going to make sense, though, as we uncover the binomial theorem and other uses of these binomial coefficients. This is a binomial coefficient 10 choose 3. So, let me ask a question. In how many different orders can I select? Select only has one L in it. How many different orders can I select n names out of a hat having n names? Oh, this is actually a pretty simple. This is a pretty simple problem to solve. I could choose them in any order that pops up as I draw these names out of a hat. So if this is totally random, I've mixed up the names in a hat. In how many different orderings could they be pulled out? Well, I reach into the hat, I pull out one name. How many different ways were there for that name to come out first? Well, there are n names. And so there were n different ways that a name could be pulled out first. Okay, if I've got Ed, John, and Martha, and there are 3 names in the hat, how many different ways are there to select the first name? 3, either Ed or John, did I say John, or Martha? Okay, so out of n names, there are n ways to select the first name. Now, you may know, if you've ever taken a class in either probability or statistics or both, you may know that the words "for every" in mathematics are a tip-off to multiply. For every one of those choices of the first name to be drawn out, how many possible choices are there for the second name? And of course the answer is there are n minus 1 names left in the hat. So for every one of these n choices, there are n minus 1 choices for the second name to be drawn out. For every in mathematics tells you to multiply. Now, for every one of these n squared minus n choices of pulling the first 2 of them out, how many ways are there to pull out the third one? And the answer, of course, is n minus 2. That's how many names are left in the hat. And all of this goes all the way down until there's only one name left in the hat. Zachary. Sorry, Zach. But there is Zachary, one name left. And so there's only one way to pull that out. It's to pull out Zachary. I shouldn't say Zachary, because then you might think they were in alphabetical order. Yeah, it was Abel. But at any rate, the answer to this question is n factorial. How many different ways and how many different and how many different orders, can I select n names out of a hat having n names? The answer is n factorial. Now, let's ask a different question. So this is question 1. Question 2 is this. If I have 5 pairs of socks, and their colors are red, orange, yellow, green, and blue, in how many different ways can I select 3 pairs of socks? I say this is a little different. I'm not choosing all 5 of them like I did all n of the names in the hat. I just want to choose 3 pairs of socks. Well, in how many ways can I select the first sock? Red, orange, yellow, green, or blue? 5. In how many ways could I select the second sock? 4. In how many ways could I select the third sock? 3. Now, and that's the final answer, 60. So there are 60 different ways. One is red, orange, yellow. One is red, orange, green. One's red, orange, blue. One's orange, yellow, red. Orange, yellow, green. Orange, yellow, blue. There are 60 choices for those 3 pairs. Now, notice that 5 times 4 times 3 is equal to 5 factorial divided by 2 factorial. Because 5 factorial is 5 times 4 times 3 times 2 times 1, but the 2 times 1 cancels here and leaves me with 5 times 4 times 3. And another way that I'm going to write that is 5 factorial divided by 5 minus 3 factorial. Since we're choosing 3 pairs of socks, that leaves 2 at the end that I'm just dividing out. Now, what's another way of thinking of this? There are 5 factorial ways of choosing 5 pairs of socks. That's 120 ways. But I'm not choosing 5 pairs of socks. I'm leaving 2 pairs of socks in the container. And however I chose the first 3 pairs, it doesn't matter what the order is of the 2 that are left. So I take 5 factorial, which is a way of ordering all of them, and then I divide by 2 factorial, saying it doesn't matter how the last 2 are ordered. So I have to divide that. So 5 factorial is 120, but if I divide by the number of ways of shuffling around the 2 left in the drawer, then that's 120 divided by 2, which is 60, okay? So in general, to choose k objects from a set of n objects, if order is important. Is n factorial over n minus k factorial. Okay? N factorial over n minus k factorial. If order is important. Now, when would order be important? Well, I might not want to wear an orange pair of socks if I'm wearing a green tie. And people are just going to look at me a little strangely. So if I want things to match and I want the order to be important, then that's the issue here. Another possibility is, let's suppose that you're forming a math club. Now, before you say, oh, God forbid, there actually are math clubs around the country. We do that here at Biola too. But suppose that you're forming an organization and you want to choose a president, a vice president, and a secretary. So if we have a club of 5 people, in how many ways could we choose a president, vice president, and secretary treasurer? Well, is that sort of like our sock experiment over here? Is order important in this example? Well, yeah, it's important to the president. So the first one that I select would be the president, maybe. Then the second one that I select might be the vice president, and the third, the secretary treasurer. So I'm choosing these 3 ordered objects from a set of 5 objects, people in this case. And so I'm going to get the same answer as I got over here. The answer is 5, choose 3. No, it isn't. We're not there yet. The answer is 5 factorial over 5 minus 3 factorial, 2 factorial, which is, we already know to be 60. Now, is that really true? Well, suppose that these are the initials of all of the people who are in the club. Then I could choose president, vice president, secretary, or president, vice president, secretary, president, vice president, secretary, president, vice president, secretary, president, vice president. There are 60 of those possible choices. Because order counts. All right. Now remember the reasoning behind this denominator. There were 5 factorial total orders of ways of picking the 5 people, but I'm not going to pick the last 2. So the order of the last two is irrelevant, so I divided by 2 factorial. But suppose now that order doesn't count. We have a club of 5 people and we want to send 3 of them to a regional conference. So in other words, order does not count. In how many ways can this committee be chosen? See, order is not important because I'm just picking 3 people and no one of them is more important than another one. They're just 3 people out of the 5. So I have my original number of ways that I could have picked all 5 of them, but I'm only taking 3 of them as a committee, so I don't care how the other 2 are arranged. But also, I don't care how the 3 are arranged. So I'm also going to divide by the number of ways of ordering the 3. ABC, BAC, BCA, CAB, CB, the 6 ways of ordering the 3 of them. This number is called the binomial coefficient, 5 choose 3. Because I've got 5 and I'm choosing 3 and the order isn't important. I'm just picking them. Okay. Now, let's do some arithmetic with this. And then we're going to prove an interesting theorem about Pascal's triangle. What is 5 factorial over 2 factorial? What is 5 choose 3? Well, like it says, it's 5 factorial divided by 2 factorial divided by 3 factorial, which is 120 divided by 2, so now we're at 60, divided by 6, so that's equal to 10. If you look in your notes, you'll see that when I drew Pascal's triangle, if I went to row 5 and slant 3, that number was 10. Notice that n choose k is the number in row n slant k of Pascal's triangle. Now, remember how that was computed in Pascal's triangle? We're going to prove a lemma. if n and k are natural, not even natural numbers, or 0, a coefficient n choose k is exactly what I said here. A number in row n slant k of Pascal's triangle. And if n is equal to 0, or if k equals n, and choose k is equal to 1. I'll explain that. If n is equal to 0, then I'm not choosing anything. So in how many ways can I choose nothing? The answer is 1. Don't choose anything. If k equals 0, then n choose 0 is also equal to 1. Okay? So n choose n equals 1, and n choose 0 equals 1, which is exactly what we said when we have 1s down the outsides of the two legs of that triangle. So proof. All that remains to show is that for the interior of the triangle, the value of an entry is the sum of the two above it. The two entries above it. Now, let's make that algebraic. In other words, n plus 1 choose k is equal to n choose k minus 1 plus n choose k. So draw yourself, well, in fact, you can look at the triangle that you already have in your notes that I drew before, and take a look at row n slant k, and then go down one more row and see which two entries are being added together. If n is, say, equal to 5, or n is equal to 4, then 4 plus 1 choose 3 is equal to 4 choose 2 plus 4 choose 3. And that's where that 10 came from. Okay? So let's prove this. And it's just an arithmetic problem, and it's not a terribly difficult one, but we have to use a sneaky trick. Isn't that a shame? Another proof by sneaky trick. Not too sneaky, but a little sneaky. Okay. Well, let's start with the left hand. We don't even have to prove this by induction. We're just going to start with the left-hand side. N plus 1, choose k, is by definition the factorial of the top divided by the top minus the bottom factorial, and also divided by the bottom factorial. Okay. Now, let's split off n plus 1. So this is n factorial times n plus 1 divided by, and I'm going to switch these around. It won't change anything, but instead of n plus 1 minus k, I'm going to write it as n minus k plus 1. That's not the sneaky trick. That's pretty baby arithmetic. And copy, copy, copy. So there's my k factorial. Okay. Now, I'm going to add and subtract something on top. Okay. This is equal to n factorial times k over n minus k plus 1, copy, copy the bottom, k factorial, plus n factorial times n minus k plus 1 over n minus k plus 1 factorial times k factorial. And the people all said, huh, what? Well, take a look at what I've done. This is n factorial times n plus n factorial times 1. And this is n factorial times n plus n factorial times 1, but minus n factorial times k, but that's no problem because I'm adding that here. So these two are still equal. And that's my sneaky trick. And now that's equal to, I've got a k up here, I've got k factorial down there, so that leaves k minus 1 factorial downstairs. And in the other one, the n minus k plus 1 cancels with the top part of n minus k plus 1 factorial. So this now becomes just n minus k factorial in the bottom. I still have the k factorial, and I still have my n factorial upstairs. Okay? Now, just one simple thing here. I can rewrite this denominator as n minus k plus 1, that entire thing factorial, and then k minus 1. I'm sorry, this is k minus 1. So n minus the quantity k minus 1, that whole quantity factorial, times k minus 1 factorial, plus n factorial over n minus k factorial, k factorial. And what does that equal to? Well, this is n choose k minus 1. And this is in choose K, and that is the end of the proof. Okay? So much for that lemma. Interesting lemma. I call it the Pascal's triangle lemma. Now, the whole point of this, as I mentioned at the beginning, was to do the binomial theorem. You may know the binomial theorem. You're going to know it real well in the next few minutes. But let's examine something. Examine the quantity a plus b to the fifth. Now, if I had to multiply that out, a plus b times a plus b times a plus b, blah, 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 5 times, that's not FOIL anymore. It's FOIL, oil. It's really a mess. I'd like an easier way of doing that. So let me ask you this question. What is the coefficient in front of the term a squared b cubed, to take one just as an example? Well, what happens? Let's write this out. We're not going to compute it because it's going to be really easy to compute in just a few minutes. But there's a plus b to the fifth. How do I get an a squared and a b cubed in the same term? Well, in how many ways are there to pick these 5 entries where I've got 2 of them matching the A and 3 of them matching the B? And the answer is pick 3 B's and 2 A's from this collection here. Well, and how many ways are there to do that? There are 5 boxes here, and I want to choose the 3 B's. Now notice, once I've chosen the 3 B's, say I take this one, and this one, then there are only these 2 ways of choosing the A. And the order is the same if I pick this one first and then this one, or this one first and then that one. So this is our old friend, the number of ways of picking 3 items out of a collection of 5 items where the order doesn't count, because B times B equals B times B. It just doesn't matter. So the coefficient is our old friend, 5 choose 3, and I can find that from Pascal's triangle. Or I can do the arithmetic, and we've done this about 4 or 5 times already this afternoon. We already know this is 10. So let's redraw Pascal's triangle down to row 5. You'll get to where you can do this very quickly. Excuse me. I'm glad I don't have to grade my own sneezes. Okay, so row 5, slant 3 is right here. But the rest of row 5 tells me exactly what all the coefficients are. Namely, a plus b to the 5th is equal to 1 times a to the 5th. And now I decrease, you just remember what John the Baptist said, he must increase and I must decrease, right? So a is going to decrease now. It's going to be a 5 for the coefficient, a to the 4th as b comes up. And then 10, a to the 3rd, and b is coming up to 2, plus the one that we just figured, 10, a squared, b cubed, plus 5, a, b to the 4th, plus 1, b to the 5th. And that is a plus b quantity to the 5th, and it's a heck of a lot easier than multiplying that all out. Now, you can also do this with a minus sign. Now, how is this going to work? You just alternate the signs. It's obvious that the a is going to be to the 5th because there's no sign in front of it, so that means it's positive. So this is going to be a to the 5th minus 5 a to the 4th b plus 10 a cubed b squared minus 10 a squared b cubed plus 5a b to the 4th. And then you can tell that minus b to an odd power is going to be negative, so minus b to the 5th. And so you can do it whether it's plus or minus. And this is called a binomial. This is called a binomial. Bi, of course, meaning two. And nomial from the Latin word nomen, meaning name. There are two names, two terms in here. And so, you also have trinomials and quadrinomials, and there are coefficients for those too, but we're not going to bother with those in this course. Okay? So, in general, the coefficient of a to the n minus k, b to the k, in a plus b to the n is n choose k. So the binomial theorem is the sum of all of those. Binomial theorem goes like this. If a and b are not 0, because if either or both of them are 0, this is pretty trivial. But if a and b are not 0, and n is a natural number, then a plus b to the n is the sum from k equals 0 to n of n choose k, and then this term, a to the n minus k, b to the k. Proof. Now, as I've mentioned a few times before, before I begin a proof, I like to figure out how I'm going to do it. Am I going to do it by brute force, meaning directly? Am I going to do it by contradiction, which would be pretty hard? Just say, no, it's not equal to that. It's equal to 7 pi over 9. Yeah, that wouldn't work. Or I'm going to do it by induction, and with all these n's in here, there's a good chance I'm going to do it by induction. So, proof by induction. Got enough room on this board to do the n equals 1 case. If n equals 1, then a plus b to the 1 is equal to the sum from k equals 0 to 1 of 1 choose 0 times a to the 1 b to the 0 plus 1 choose 1 times a to the 0 b to the 1, which is equal to a plus b, and that one works out. Now, let me erase this other board, and we'll see how much room it takes me to do the rest of this proof. Okay, so suppose this statement is true for some m natural number. Okay, so in other words, a plus b to the m is equal to the sum from k equals 0 to m of m choose k a to the m minus k b to the k. Suppose that's true for some m. And by the way, we know it's true for that m. My job is to show that it's true for the rest of the m's, for m plus 1. So we do this the way that we've always done it. A plus b to the m plus 1. And what is that equal to? Now we're on planet m plus 1. What do we do when we get to planet m plus 1? We look back to planet m and split off what we have to split off. So we're going to split off m of those little monsters. So let's take this one, a plus b, and the rest of them, a plus b to the m. That's certainly true. And now we use the induction hypothesis. The induction hypothesis is that this statement holds for this particular part of the product. So copy, 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 and then copy, copy. Okay, so far so good. Haven't done anything yet at all except write down the induction hypothesis. Now, let's use the distributive law here and write this as the sum from k equals 0 to m of m choose k times a to the n minus k plus 1 now, because I'm multiplying by a, times b to the k, plus this other sum where I'm pulling in the b. So this is the sum from k equals 0 to m of m choose k, a to the m minus k, b to the k plus 1, because now I've pulled the b in. So I've got the sum of those two sums. Okay? Now, what I'm going to do is I'm going to pull out the k equals 0 case. So pull out the k equals 0 case. From the first one. Well, when k is equal to 0, what is this? This coefficient is 1. This is a to the n plus 1, b to the 0, so this is just a to the n plus 1. Plus, and then the rest of this noise, that's from k equals 1 to m. Of m, choose k, copy, copy, copy. No, I'm sorry, this is not an n, it's an m. Okay. This is a to the m minus k plus 1 b to the k plus, and what I'm going to do in the second one, I'm going to pull out the last one, where, so this is from the first sum, and I'm going to pull out the k equals m case from the second sum. I'm going to separate it out. So this is going to be, well, k is equal to m, so that's b to the m plus 1. This is 1, this collapses. Plus the rest of this, which is the sum from k equals 0 to m minus 1 now. And then this is m choose k, a to the m minus k, b to the k, plus 1. Just copying over, this is b to the k plus 1. Okay. Now, copy, copy, copy. So this is a to the n plus 1, a to the m plus 1. This is an m also, sorry. There are no n's in here, they're all m's. Okay. So that's a to the m plus 1 plus, and I'm going to copy over this stuff, the first sum. So that's k equals 1, m choose k, a to the m minus k plus 1, b to the k, plus, and copy, copy, b to the m plus 1, plus, but now, what I'm going to do, this is another little sneaky trick. Instead of summing from k equals 0 to m minus 1, I'm going to sum from k equals 1 to m, but I'm going to cut all of the k's down by 1. So this is going to be the sum from k equals 1 to m of m choose k minus 1. So k minus 1, it would start at 0 just like this did, and it would end with m minus 1 just like this one did. Times, okay, so m choose k minus 1 times a to the m minus k, and that's k minus 1 in parentheses now, b to the k. Okay, so we're making big progress here. Okay. Now notice that this is a to the m minus k plus 1, and this is a to the m minus k plus 1, b to the k, b to the k, so those are the same. So this is equal to, and I still have a to the m plus 1 outside, plus, and by the way, at the tail end, it's going to be plus b to the m plus 1, so I don't forget to put that one in. But inside now, I can combine the sums from k equals 1 to m of m choose k plus m choose k minus 1 multiplied by this same thing, a to the m minus k plus 1, b to the k plus b to the m plus 1. But now, by Pascal's triangle lemma, I know what the sum of those coefficients is. So this is equal to a to the m plus 1 plus the sum from k equals 1 to m of m plus 1 choose k, a to the m, and I'm going to move this back around so it's m plus 1 minus k. This is still b to the k. And oh yeah, our old friend b to the m plus 1. But now I can pull this back in and go from 0 to m. And I can pull this back in and go to m plus 1. And so this is going to be the sum from k equals 0 to m plus 1 now of, copy the coefficient, m plus 1 choose k, a to the m plus 1 minus k, b to the k. And this is exactly the binomial theorem for m plus 1. And that is the end of that proof. Let's do an example or two. Okay, and then we're going to totally change topics, so we'll be done for today when I'm done with this. So, example. Find the coefficient of x cubed in 1 minus x to the 5th. Okay, 1 minus x to the 5th. So, which version of the binomial theorem are we going to use? The plus or the minus? Obviously the minus. And you remember that a minus b to the n is equal to the sum minus 1 to the k from k equals 0 to n of a to the n minus k b to the k. Okay, so this is the binomial theorem for if I have a difference. And again, this just comes because if k equals 0, it's positive, and that's obvious. If k equals 1, it's negative, all the way out to if k equals n, then it just depends on whether n is even or odd as to whether it's positive or negative. But this is the binomial theorem for the difference. So here, in this example, 1 minus x to the 5th, what does n equal? Hopefully a few of you said 5. Okay. And what is k? Well, notice that b to the k is the power of the last the last of these two terms, the second of these two terms, that's the x. So k is indeed 3, since I want the coefficient of x cubed, right? So what's this coefficient? So here comes the answer. Minus 1 to the k to the 3. A, which is 1, it doesn't matter what the power is, but I'm going to write it anyway. 1 to the 5 minus 3 power times x to the 3, which is equal to minus x cubed. So the coefficient, I'm sorry, there's one thing missing. Please correct this in your notes. Stop, kill the power, go back, correct this in your notes. I left out that very important binomial coefficient. N choose k. N choose k. Minus 1 to the k, n choose k, a to the n minus k, b to the k. So in here I've got 5 choose 3 times 1 squared, which is equal to minus 10 x cubed. So the coefficient equals minus 10. That could have been a disaster. Hopefully everybody corrected this in your notes, and nobody was off getting chips and dips while that came up. So, and if you're the only one in the room that got that correction, sell it for $1 a pop. Because during these times you have to make money any way you can, as long as it's honest, right? Okay, let's do another example. Find the coefficient of x cubed in 2x minus 3 to the 5th. Okay. So we're still going to use the a minus b formula. And of course, once again, n is equal to 5. K, now the x cubed appears in this first term of the binomial expression. And so the first one is to the n minus k power. So k in this case, if I want this to be x cubed, k is going to have to be 2, so that 5 minus 2 will be the 3. So k is equal to 2 in this case. All right, and then I just copy. So the answer is minus 1 to the 2, which I know is plus 1, but I'm writing it so you'll know that I considered it. N choose k, which is 5 choose 2, a to the n minus k, which is to the 3rd. So 2x, that quantity to the 3rd, is 8x cubed, times b to the 2. So b squared is 9, which is equal to plus 1. 5 choose 2 is 10, times 72. I'm sorry, k is 2. That's right, good. And that's an x cubed. So the coefficient is 720. Okay? So, hopefully that's understandable to you. If not, you know my phone number. Give me a call, and I'll be happy to answer questions. We've been having good office hours by telephone with people. So jump in there and be a part of that. And God bless everybody. Keep yourselves well. And we will hear each other next time. Goodbye.